In the bigger picture of equilibrium systems, solubility is a pretty important topic. And what we're looking at now for solubility is not qualitative like it was with our double replacement reactions, where we just said, oh, something is soluble or something is insoluble. In reality, it's not binary like that. Things are either kind of soluble or less soluble, or maybe really soluble and really not very soluble. But there's always some solubility, and it has to do with the balance of equilibrium systems where you can't have a zero. So we'll address that in more detail in a little bit, but I just wanted to mention this is qualitative. We can do it quantitatively with our solubility products in aqueous dissociation equations. We've defined solubility before, but I just want to mention right now a few steps in that hierarchy. Solubility, if we wanted a super cheap definition, we'd just say like ability to dissolve. And I think it's worth having this discussion again now that we had previously, and that is the different levels, we'll say, of dissolving and the pictures that go along with it. And then we'll talk about what solubility means in the context of these equilibrium problems. So let's start out with dissolve, right? When we're talking about the raw idea of to dissolve, we're talking about separating particles by overcoming intermolecular forces. Separating particles by overcoming, intermolecular forces. And we're not talking so much intramolecular forces, chemical bonds, we're talking about the intermolecular forces. So a simple example of that might be something like common table sugar, sucrose, which is C12H22O11. And that's sucrose. You've probably seen at a restaurant or whatever, and maybe in the cartoons when they're drinking tea, this idea of a sugar cube, which is really just a bunch of sugar molecules attracted to each other by intermolecular forces. And so it's annoying to write this, but I will. C12H22O11. This kind of implies a simple cubic structure, but I'm not implying that, even though it looks like it. You get the picture. So we'll say we have sugar molecules at each vertex on this, and that's what a sugar cube is like. And what holds these particles close together, or any distance apart, are the intermolecular forces. In this case, this has got some dipole-dipole forces and some London dispersion forces, and that pulls those particles together well enough that at room temperature, sugar is a solid, right? Sucrose is a solid. If we put it into water, we get a different picture of how things work. It dissolves. It doesn't dissociate, but it does dissolve. So this will be our beaker with water. I was very negligent in my color choices. There's our water. And now what are these sugar molecules doing? Well, they're not arranged like this anymore because the attractions that had pulled them close together in a specific arrangement have been overcome by the waters. And so you got like C12H22O11, and maybe you got like a C12H22O11. Maybe you've got, C12H22O11. And although that picture is semi-pointless, what I'm really saying is the particles moved around. The particles didn't break apart, the molecules didn't break apart, but they got farther apart as the intermolecular forces were overcome. So as we look at this, this is a distinct case of dissolving, right? The intermolecular forces were overcome, but the molecule remained intact. So what really happened here, the molecules got farther apart. So when we dissolve here, we're talking about the molecules getting farther apart in solution. The molecules are not separated. So that's our basic idea of dissolving, right? Now there's a subcategory of dissolving that's very important for electrolytes, and that's for ionic compounds. When they dissociate into ions, they separate into ions. So let's just draw this down here. We have dissolving, and then we have this idea of dissociating. it is still overcoming intermolecular forces, but it's overcoming specifically ionic forces, right? So this takes some ionic compound, and that is an electrolyte. And we've defined that before, something that breaks down into ions that allow charge to be carried in a solution that's conducting electricity. Ionic compound separates into ions in solution. So if we look here, the intermolecular force we are overcoming is ionic, right? And then we have the ions separating. So the key idea there, if we look at molecules getting further apart versus ions getting further apart, when ions get further apart, then we don't have that ionic compound anymore. We've just got ions floating around. So in a very similar looking picture here, we'll do NaCl. So we've got some sodium ions and some chloride ions and some sodium ions and chloride ions at all these vertices. And in reality, that goes off indefinitely in 3 dimensions. That's a beaker. I'm sure that makes it look much better. We've got our water, a solution. Instead of having a bunch of NaCls next to each other in the solution, though, we have sodium ions, and we have chloride ions, and we have sodium ions, and maybe we have like chloride ions, and they're just separate now in this solution. Maybe you got some sodium ions, chloride ions, they are farther apart. So when we're talking about something dissociating, we're talking about ionic intermolecular forces are overcome. And what that results in is ions, separating ions in solution. And when these ions can be separated, when we can dissociate an ionic compound, we call that an electrolyte. And we have strong electrolytes and weak electrolytes, which takes us full circle to our solubility. Strong electrolytes are fully soluble. Weak electrolytes are not fully soluble. They're less soluble. And the definitions get a little overlapped. So dissolving and dissociating, it is a rectangle square scenario. All squares are rectangles, but not all rectangles are squares. So all dissociating is a subcategory of dissolving. Not all dissolving is dissociating. All right? And we can look at this. Dissolving is our supercategory, and dissociate is a subcategory. A special dissolving. And with all that in mind, we now have these 2 vocabulary terms, dissolving and dissociating. I want to talk about calculations of solubility. And we aren't going to look at it in this video, but we've looked at it plenty in other places. The idea of why things are soluble or insoluble in other things, polarity, and things like that. What I want to talk about now is a slightly different definition of solubility, and that's something we're not usually looking for. But in the context we are going to use, solubility is not necessarily just a property, an ability to dissolve, but it's a value, okay? And so the idea for our solubility here is going to be that it is some saturated concentration. The solubility, this word, solubility, is going to be a saturated concentration. Okay, so solubility can be a property, right? The ability, I guess I should say, the characteristic, the ability to dissolve, and we can describe a saturated concentration when you have as much as can be dissolved as possible at a given temperature. We call that a solubility. And with that, we have these things that are solubility constants. Ksp is our solubility product. And that is our equilibrium constant for, in this case, our dissociating, for electrolyte, dissociation. And so a simple example of how this would look, and we'll work into specific examples in a minute, but if you just have something that's insoluble, some metal with some anion that's insoluble, it dissociates in solution to give you some metal ions and some anions. And we would have a KSP, an equilibrium expression, that is some concentration of metal ions times some concentration of the anions. All right, so this is how our solubility expressions are going to look. This S that we will have, saturated concentration, solubility, S, that's going to be calculated using the equilibrium constants, the solubility constants. And so we'll do some examples of that, and then we will move on to many other examples.